Okay, so now I want to drive you through an exercise. So you consider like the general problem of state discrimination. So you are given a collection of states, which are rho XX included into the A, and the distribution rho X, distribution P of X. The goal is to compute the maximal probability um, with which you can discriminate the ensemble. So this maximal probability with which you can discriminate the ensemble would be called like rho gas of px, and yeah. And so the question is like, suppose you have a quantum channel going from LA to LB. But you must prove that the probability of guessing px is like superior to the probability of guessing probability of x epsilon of rho x. So what you can see here is like it's more or less evident. Like if you do not have a channel, then you do not lose information, and if you do not lose information, like here there is more information, and so if there is more information, the probability of you being right is okay, you know, like it will be superior that if you lose information. If you have more information, then you will normally do always better than if you have less information, unless you cheat. So yeah, you are like this, and so you just prove intuitively this inequality, but let's prove it a little more further. So as we see on the course, like in the other videos, sum of x. So the probability of this is just equal to the sum of x of sum of px of the trace of mx rho x or rho x mx, such that the sum of x of mx is equal to y. So the sum of the probability sums to 1, and mx is semi-positive definite. And so if you just consider now like any feasible point believing into LB, so let's call it MXX, that believes into LB for p guess of rho probability of x of epsilon of rho x, then we just have that sum of x of px of the trace of nx with epsilon, like with the channel applied in rho x, but it just equal at the end of sum of x of px of the trace of epsilon dagger on the channel of rho x. That's equivalent, that's a property of a channel. And so because of that, like we have this, and so we just need to see like we just rewrote in a way like, you know, the initial strategy with a channel, And so we have this, and we just need to see if it respects the properties of being semi-positive definite, and if the sum of x of mx is like equal to um, like being like sum of like it's like the sum of x of epsilon dagger of nx, and if it respects the property of this and the sum of x of mx being equal to I, and so this is equal to this, and so this is equal um, to normally this, because like it's just like a property once again of the channel. Like if you apply all matrices first or matrices by matrices and after the channel, it's equivalent. And so this, as we saw, should be I. And so we just need to prove that this is equal to I. And so for doing it, it's like we just take like the definition of the trace, and the trace of epsilon and x is just equal to, more specifically, like the trace of epsilon p of the channel digress on p. It just at the end the trace multiplied by I by epsilon dagger of p, but we can apply the trick of putting like more like this, like we can do like this, and we apply the same trick of putting channel at the beginning, and so it just trace of epsilon dagger of e multiplied by p, and so for having like this, then you need to like remember that it's CPTP, a channel completely positive trace preserving, so it means like the trace of epsilon of p should be equal um, trace of string layer of p stroke of like the trace of epsilon of p should be equal to the trace of p, and so it just means that epsilon dagger e should be equal to e, so we have trace of p, and so which means that it's equal to I. And so we just respect the two property, but as we write the channel proba as a case that could be represented into to not channel case, like, and we check about sub. It just proves that the probability of guessing x by x is superior to 0. yes of px, some p of x.